So, good morning, students. So, this is our fourth lecture in our complex lecture series, and the topic for today's lecture is programmable logic devices, ROM, PLA, and PL. So, we'll be very quickly covering how these three programmable logic devices can be used to design combination circuits, which we have designed already in our unit 2 in form of combination circuits. So, these are the contents. PLD's introduction. So what are programmable logic devices, how they can be used, and then covering ROM, PLA, and PL to design some questions. Okay. So these are the three: ROM, PLA, and PL. ROM stands for read-only memory, PLA stands for programmable logic array, and PL stands for programmable array logic. So this is a basic difference in ROM and array and part of the circuit is fixed. So that's why we are using a decoder, because decoder can provide me fixed number of AND gates. Okay. But the OR part is programmable. That means it can be decided by me. How many number of OR gates are to be used? What are going to be the inputs for those OR gates? So this is all within the user's control. And then coming to PLA. PLA is offering me both programmable AND array and programmable OR array. And in case of PL, AND array is programmable, OR part is fixed. So this is the basic difference between the three programmable logic devices, ROM, PLA, and PL. And in 2 marks, the question can be asked, what are the different types of ROM? Then these are the 4 different types of ROM. PROM, that means programmable read-only memory. The ROM which can be programmed once. Then MPROM, mask PROM, the ROM which can be programmed once by the manufacturer, and then no more programming can be further done on that ROM. So this is PROM, but it is M stands for mask. That means it is masked for further programming. That means no further programming can be done. Then EPROM is erasable programmable read-only memory. That means the content once written on the ROM can also be erased if required. Then EEPROM is electrically erasable programmable read-only memory. That means the mechanism used for erasing the data which has been once written on the PROM is the mechanism which is using the electrical current for erasing. So that means there must have been some another method by which the erasing can be done. So another method is the use of UV rays. So, but this is more prominently used EEPROM, which is also known as E square PROM. Okay. So this is the basic of this ROM, and now let's proceed towards the circuit designing part. So circuit designing using ROM. So the basic thing which we require to design a ROM is requirement, min-terms are required, and a decoder is required. साइज जो है वो आपको डिसाइड करना है, साइज टू बी डिसाइडेड, and then OR gates equal to number of outputs. Okay. So let's say we are provided with an expression f1, which is a function of a, b, c is equal to summation m 0, 1, 4, 6, let's say, and then f2 is also there, then a, b, c, which is mentioned as 2, 3, 6, 7, and then f3 a, b, c is mentioned as a bar b c plus a bar b bar. So the first thing which we have to recall is that I need min-terms. So here min-terms are provided, here min-terms are also provided, but here min-terms are not provided. So for this expression I have to calculate the min-terms. So to obtain the min-terms I have to convert this into canonical expression by multiplying this a bar b bar with c plus c bar. Okay, so the expression becomes a bar b c plus a bar b bar c plus a bar B bar, C bar. So if we replace these variables by 0 and 1, so because bar is there, so replacing it with 0, without bar with 1, again here also, and then 0, 0, 0. So this 0, 0, 0 is equivalent to 0, 0, 0, 1 is equivalent to 1, 0, 1, 1 is equivalent to 3. So the minterms for this F3 becomes 0, 1 and 3. So this is the basic requirement to design circuits using ROM. Then I have to choose a decoder, and size is to be decided by me only. So if we decide that the decoder inputs is equal to number of system inputs which is to be designed. So here we can see that there are 3 inputs. So that means decoder must be having 3 inputs. So if a decoder is having 3 inputs, then outputs will be 8. So that means I am going to use a 3x8 decoder. Okay. So let's use a 3x8 decoder. So 3 inputs will be there. A, B, C. It will be 3x8 decoder. So 0, 1, 2, 3, 4, 5, 6 and 7. So this is a 3x8 decoder. So I have come to the second step and decided that I am going to use a 3x8 decoder to design this circuit. Then number of OR gates to be used. Number of OR gates is equal to number of outputs. So we can see that there are 3 outputs, F1, F2 and F3. So there are going to be 3 OR gates. Okay. So there are going to be 3 OR gates. F1, F2 and F3. Okay, and simply draw a vertical line which is crossing the decoder outputs. So there is a matrix available to me now at the output section which can be used to program as per my requirements. So let's program this ROM. So for F1, we can see F1 is having minterms 0, 1, 4 and 6. So for this F1 first OR gate, so 0, 1, 4 and 6. So these 4 outputs are going to participate in designing of F1. Similarly, then proceeding to F2. F2 is 2, 3, 6, 7. So this is 2, this is 3, this is 6 and 7. And then F3. F3 is having minterms 0, 1 and 3. So this is 0. Then 1 and then 3. So this is how we can design a circuit using PROM. Okay. Now let's proceed towards the circuit designing using next programmable logic devices, which is PLA. So PLA says requirement is minimize the expressions. Okay, so let's say we are provided with F1 is equal to A bar B plus AB bar. F2 is equal to, let's say we are provided with 0, 1, 4, 6, 7 and F3 is A bar B, C bar plus A bar B. So I need minimize expressions. So this we can say that this is already minimized. Okay, this is already minimized because it is equivalent to XOR gate and it is canonical also. This we have to solve K-map for 3 variables. So quickly solving it. So 0, 1, 2, 3, this is 4, 5, 6 and 7. So if I check the grouping patterns, I can see that I can simply make this one and this. So there are 3 groups. Okay. So if I write the answer for this A, B, C, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. So this is K-map solving, which is already a topic which is extensively utilized in our subject from unit 1 onwards. So I'm not going into the details of the K-map. I'm assuming that K-map is known to us and we can solve K-map for any given Boolean expression. So let's write this expression as F2 is equal to, so for this one, I can write B bar, C bar. For this one, I can write A bar, and this 0 is common. So A bar, B bar, and then last, this is corresponding to this A, and this is B. So A, B. Okay. This is not a canonical expression. So first we have to convert into canonical expression A bar B C plus A bar B into C plus C bar. That is into C plus A bar B into C bar. So there are min terms, which this is redundant because they are repeating. So I can cancel this out. This is 0, 1, 1, and this is 0, 1, 0. So 0, 3 and 2 are the min terms. So either I can solve K map, or I can simply take B common from here and then B and A bar B, sorry. So I am taking A bar B as common, and it will become C plus C bar, which is equivalent to 1. Okay. So ultimately the answer is A bar B. Okay. So I can see now that all three expressions are minimized. So all three expressions are available to me. Let's highlight these expressions. So this is F3, and this is my F2, and this is F1. Okay. So I have to check how many products are there. Number of unique products. Number of unique products. So there are products. This is product number 1. This is product number 2. This is product number 3. This is product number 4. This is product number 5. And this A bar B is repeated here. So this is not a new product, but it is already product number 1. So ultimately, number of unique products are 5. Then we have to prepare the programming table. So programming table says, write the number of products, which variables are going to be used in it, and these products are to be used in which all outputs. So the first product is A bar B, second product is A B bar, third product is B bar C bar, and fourth product is A bar B bar, and the last product is A B. So these are the 5 products, 5 unique products, and writing it in form of ABC, A bar B, that means A is 0, B is 1, C is not there. A B bar, that means A is 1, B is 0, C is not there. B bar C bar, that means A is not there and B and C are 0. A bar B bar, that means A and B both are 0, C is not there. AB, that means both are 1, C is not there. Okay. Now the first two products, these are going to be used by F1 and F2, and F1 requires no other product. Then F2 says it is going to require the product number 3, 4 and 5. So product number 3, 4 and 5 are going to be used by F2. These two are not required for F2. And F3 says it is requiring a single product A bar B. So A bar B, that means it is the first one only. So F3 requires only single product and no other product is required. So this is the programming table for this given problem. Okay. Now we can realize the circuit using this. So I am requiring 3 variables. So A, B and C. So this is the structure of a PLA. To realize A bar and A. Similarly, from here we can realize B bar and B. Then C bar and C. Okay. Then I need 5 products. So I need 5 products. 1, 2, 3, 4, and this one is 5th product. So these are my products. Now I'm going to use 3 outputs. So there are going to be 3 sums. Okay. So this is a blank PLA. Okay. Now we will start programming it as per my requirements. So let's program this as per my requirements. I can see now that first F1 requires first two products. So F1 requires first two products. F2 requires last three products. So last three products. And F3 requires only first product. Okay. So this is the programmable OR part. Okay. Now let's proceed to the programmable AND part. How this product is going to be realized? A bar B. How I am going to realize this first product? Let's label them as 1, 2, 3, 4, and 5. And this is also the product sequence 3, 4, and 5. So first product is A bar B. That means this is A bar and this is B. Second product is A B bar. So this is A and this is B bar. Third product is B bar C bar. So this is B bar and this is C bar. Fourth product is A B bar. This is A and this is B bar. Sorry. A bar B bar. Sorry. So this, there is a correction in it. So fourth product is A bar B bar. Fourth product is A bar and this is B bar. And the last product is AB. So this is A and this is B. Okay. So this is how we can realize circuit using PLA. This is a simplified realization actually, but in actual there are XOR gates also available at the output of these OR gates. And these XOR gates are used to invert the expressions. Okay. 0 and 1. So it is known to me if in an XOR gate one input is 0, the other input reaches directly, and in an XOR gate if one input is fixed to 1, then the other input is complemented. Okay. So in this case I am not requiring any complement operation because F1, F2, F3 all are directly available to me. So F1, F2, all these three, F1, F2 and F3 are going to be connected with this 0. So this is how we can design circuits using PLA. Now let's proceed to the PAL part. So let's say I'm going to design the same question using PAL. Okay. So what all corrections do we need to make? So in PAL, the only difference is, again, requirement is minimize expressions. OR part is fixed. And if OR part is fixed, that means I will not be requiring this XOR section. Okay. So this XOR part will not be there. And if OR part is fixed, that means these crosses can't be there. So in place of these crosses, I can use permanent connections in form of dots, which we have been using in our unit 1, 2 and 3. Okay. So XOR part is not required. That's the first change between PLA and PL programming. And the next part is the crosses which were placed in the OR array in case of PLA are going to be replaced with fused dots. That means permanent connections. So this is how we can design circuit using PL. Rest everything is same between the PLA and PL programming. Okay. So with this we come to the end of this programming part using PLA and ROM, PLA and PL. Thank you very much.